All right, hello everyone. I'm going to take a brief moment and talk about Exam 1, which is happening this week. Exam 1 will work actually quite a bit like the quizzes, where it'll be posted online. The only difference is between Exam 1 and a quiz is that it's longer. It is timed versus the quizzes were not timed. And you shouldn't be consulting any other classmates or the internet or anything like that. So I'm going to post it at 5 a.m. on Wednesday, 9:30, and it will be available until 5 p.m. on Friday. So anywhere within that time range you can take Exam 1. And that means that if you were going to start it on Friday, don't start it at 5 p.m. You need to start it at 4:10 p.m. because there's 50 minutes and you have to have it completed before the deadline, right? So if you're a real procrastinator, I guess shoot for 4:10 p.m. Friday. I think you'd be better off doing it before then myself. But the 50-minute time limit starts as soon as you start the exam. I'm guessing between 35 and 45 questions. I don't quite have it totally written yet. I just did a 60-question exam for the Con 151, and it seemed like a lot of people did not have enough time, is the feedback I got. So I'll make this one a little bit shorter. Looking at quizzes, it does seem like you guys take a little over a minute or a little bit more than a minute per question. So you should have time, but I still think that it would be beneficial if you had your notes together and you could answer some questions without consulting your notes. That way you wouldn't need to go through and try and find all the information. I guess I can skip ahead since I just brought that up. It is an open note, open book exam, so you can't seek answers on the internet. You can't ask your classmates. It's not a group exam. Don't have a local engineer working with you or anything like that. The most important thing, it does cover multiple chapters from the book, but the most important thing are the PowerPoint presentations and the video recording. So if you haven't been watching the videos on YouTube, you might want to go through. That'd be a good review just to watch those videos. Also, anything that came out of the labs. So working through those through the labs, and we really only had the one concrete testing lab as far as in the lab, and many of you will not take that until, well, half of you won't do it until this week. So when I say the labs, it would be more like the measurement lab and the stress strain plotting lab. Let's see, there will be some calculations, so it'll be similar to the quizzes. So have a calculator ready. You don't have to spend time trying to find your calculator during the exam. As far as the book, it covers chapters 1, 4, 13, 14, 15, 18, and 20. I've taken little bits of quite a few chapters, and that's why I think it's more important to focus on what we actually covered in the PowerPoint. So I'm not going to ask you anything that we didn't cover in the class, so it's not some random obscure thing from chapter 15 or something. So looking at this brief overview, we started with atomic theory, how we classify materials, what about their compositions. Are they identified as a compound or an alloy or a mixture? Are they natural versus man-made, meaning can they just found in the natural environment, or do we have to actually manufacture the material? Is it organic versus inorganic? Basically, organic means it's carbon-based, right? What's the bonding mechanism? Because that'll affect the material properties. Is it ionic bonding, covalent bonding, metallic bonding? What are differences between those types of bondings? And then in general, molecular structure and what different molecular structures look like. And I want to say we had a number listed for steel in itself on one slide. So when we talk about specifying materials, how do we specify materials? There's different classes based on material properties, things like strength or color or how well they conduct electricity. So that was basically just one slide that had all the different classes and the properties related to it. What about standards? Who's writing the standards for different disciplines? We had some slides based on your electrical standards or acoustic standards or whatever standards you're looking at. Who's writing them? And ASTM is kind of the governing one that's writing all of them, right? And especially with the testing mechanisms of those standards. So, but the ASTM is broken into multiple sections. What are those sections? And so you could find out material. You can figure out what section you would go to figure out the specifications for a particular material. Then we moved on to the mechanical behavior of materials. Be familiar with the 5 types of forces. Remember those? We have tension, compression. We have bending, which is a moment. We have torsion, which is a shear. Which is torsion, which is a twisting. And then we also have a shear. Be familiar with what the general idea of stress is. It's force over area. Now, this is a tensile stress when we're pulling it. We labeled that as a sigma, and we have it as P over A. I think in class I actually did F over A, P over A, F over A. Each one of those means a force, right? As far as units, it would either be in kips per square inch or megapascals, which is a Newton per millimeter squared, if you're following your units. We haven't done as much in metric, so I'm trying to keep any problems where you actually have to calculate something in standard units. So I'm trying to help you out whenever I can. And related to stress, we have this idea of strain. How much is the object elongating? In our equation for strain, we have this little e, which is like an epsilon, and it equals the change in length. That's our L minus that's our final length minus initial length, L minus L0, divided by our original length, L0. Units on that are unitless, but we actually put them in there as either inches per inch if we're in standard or millimeters per millimeter for a metric. Also be familiar with how we find the relationship between stress and strain with this idea of a stress-strain testing machine, right? Universal testing machine. From that, we end up with a stress-strain graph. Know the regions: elastic, yielding, strain hardening, necking. Know the key stresses: yield, ultimate, failure stress. Know how to find the slope of the elastic region, or what, more importantly, what that is. That is the modulus of elasticity, which gives us our fundamental relationship between stress and strain for that given material. What's the difference between a material that's ductile and brittle as far as our stress-strain diagram? And what about resilience and toughness? One of those is the total area under the graph, and one is just under the linear section. Know which one is which. Heat treatment. What is it? Why do we do it? Why do we care? 3 stages to the process. We're heating it up to a certain temperature. We're leaving it at that temperature for a while, and then we're quenching it. That's basically what it means by the 3 stages. What are the types of heat treatment? Be familiar with those. What about the definitions of pearlite, decolescence, austenite, recolescence, martensite? So what do those mean as far as the heat treatment process and the material properties during that process? What about tempering, annealing, and normalizing? What are they, and why do we do them? Those are all good possible questions. Then our last section was shear stress. So we said shear stress, similar to our linear axial stress, which was sigma is equal to the force over the area. Well, this is shear, which is our shearing force, V, over the original cross-sectional area, right, or sheared area. So the equation tau is equal to V over A. No, I didn't put the units in there. It's the same units as our other stress. It's either in kips per square inch or megapascals. With that in mind, we started talking about connections and different type of connections. Could you identify a single shear versus a double shear load on an object, right, on like a bolt or something? And you need to know those because if you're figuring out how much shearing stress is on that object, if you have 2 shearing planes, meaning it's in double shear, you'd have twice the area than if you had 1, right? We also talked about shear rupture. This was when if you had a bolt too close to the edge and it took out a block of material. What is the area that was broken out? So that's where you had to take the depth of the material times how far back it is by however many different planes are actually sheared out. So it could be 1, 2. I don't know if you could do 1, but at least 2, maybe 4, maybe 6, so on and so forth. So know those connections as well. So that's what I have. Look through all the PowerPoints. There's not a whole bunch on this one, but if you have any questions or anything, reach out, let me know, and I'll talk to you all later. Thanks.